When people talk about robots, they normally think about what you see in the movies, these flashy lights robots that go out to all these sorts of shenanigans. But in reality, this is not what robots are. At the heart of robotics is automation. Robot comes from a Russian word that means forced labor. This means that the peasant work and this low-level work that these people were doing, they try to fix by introducing a robot, as robots can eliminate these tedious tasks to free up more creative work. And that's what the heart of robotic is, by getting rid of these tedious tasks and automating them. As such, I would like to introduce you my personal passion project, Fiddy ARMOR. ARMOR stands for Autonomous Reaching with Machine Object Recognition. And our goal for Fiddy ARMOR is to eliminate the tedious tasks of packing by introducing computer vision, as computer vision is the newest technology that's coming into the world today. And computer vision works by giving cameras and giving them to robots and giving them the ability to see. Because as humans, we're able to interact with our environment because we can see everything. By giving robots this ability, we can drastically improve their capabilities. And as such, I want to eliminate the tedious task of packing. How my project started was a Raspberry Pi. A Raspberry Pi is a single board computer that is just like your laptop, just like your PC, but a very small and cheap version. And it's able to still have Wi-Fi capabilities, it's able to interact with USBs, and it's still powered by the wall, but it's small and has these extra pins that go along the side like this. These pins are able to be programmed to receive data, to spit out data, to have power and ground, and can interact with servo drivers and servo motors. And servo motors are these motors that are able to move with accuracy to certain levels of degrees. And they are the core of how my system runs. Even though my system is a computer vision based system and is showing the technology of computer vision, I need it to be able to interact with a robot. And as such, I used the Raspberry Pi with its both ability of using USB cameras and running powerful computer vision technology, and also its ability to interact with these amazing robotic systems to integrate them together. This started with having the code, where it was using Qt Creator. This is a very common software, especially for computer vision. This is a coding platform where you can code in various different coding languages. I picked C++ personally for its wide range of support in both computer vision and general coding. By using OpenCV, an open library of all the different computer vision technologies where we're able to interact with the visual feed and stuff, I was able to import this library and start coding on these cameras. And I was able to use these cameras to observe the environment and determine stuff, and determine, is this an object? What's the depth of this object? And what's the most common color, etc., etc. And with this, I was able to start the basics of the Fiddy ARMOR project. How this works is we have two cameras at set locations, and an object will appear in the middle of these cameras. When it has appeared, it will calculate its pixel length. It will go as height, width, and length in pixels, because it can count each pixels of its most dominant color. For starters, I used red objects and see which is the most amount of red objects in a big grouping. With this, we're able to use a set square marker, which is a separate marker that the eye and the cameras can see, with a set length and width of 25 mils. With this marker, we can know how big it is because I've already told the system. And so it can measure the pixels of that. If it's 25 by 25 millimeters, but it's actually 75 by 75 pixels, we can divide the both to find a ratio to pixels to millimeters. So when we have our next object be aligned with it, regardless of its size, we can figure out its size. We can figure out what's actually its size, because even though you can see me, you don't know how big I am. You know roughly how big a human is, but do you actually know how tall I am? Do you actually know how big this hairbrush is? Is it massive? Is it small? You don't know. So we're trying to give the robot the ability to figure this out. With this figured out, we're able to now integrate a physical interactive software. And as such, I designed first a conveyor belt. This conveyor belt was fully 3D printed like everything in this project due to my passion of 3D printing I've had for many, many years. As such, it took a lot of time, as normal conveyor belts are made of latex and very powerful and expensive technology. And I had to make it out of cheap PLA, plastic, used in 3D printing, as I'm just a student with a small budget. That's why I had to use a small Raspberry Pi. But it's still deemed effectable. Just like how the cameras were still good enough, even though they are cheap cameras, my plastic was still able to develop a good system. It was noisy and it got jammed a few times, but with a little bit of grease, it was able to be smooth and able to work. And we were able to have a system that was able to move an item into camera view. Once it was viewed, it was able to detect it with the cameras, and then it was able to know its height and width and length. With this, we're now able to integrate the robotic arm. This arm was able to then figure out its position based on where the cameras can see it. It's figure out its X and Y position and move to it using inverse kinematics, a complicated software to help reduce, complicated mathematics I should say, to help reduce the load of coding. So you have to code each individual step. Rather go, I'm here, I want to go here, grab. With this inverse kinematics in place, we're able to move the arm to the object and then adjust the claw based on the size of the object and move the object to the correct location, which is already a successful project. We're able to develop a system that's able to detect objects and move them based on their size, based on their location, and means that we're able to adapt to the environment. So if the object moves in a different position, if it falls into a different location, it's still able to pick it up. If it's a random size, it's able to pick it up. We've developed a system that's already better than the other technologies out there, like the common Amazon robot that started being built and was released during my project, where they have to have the whole catalogue of Amazon items to be able to recognise an object. And this is a very tedious task, where they have to employ people to measure every single object that they pack with these robots and to import all their details. In comparison, I have my system that is successful and works on any object. All the system was able to meld into a product. As this works by having two cameras that watch for an object to come on a conveyor belt. When the object is on there, it will measure its height, width and length, and then it will pick up the object depending on its height, width and length. It will adjust to the right claw size and move it, which is a successful product. And it worked amazingly, and this worked by having a set square. This was a square that had a set height and width of 25 millimeters. And then when the camera saw that, it can then measure its pixel height and width by saying, well, I've taken a picture of this item, and I go and I'll look for it on the screen. And the second it found it, it'll go, haha, that's our template. It's a very distinct item that you wouldn't see in the natural packing system. And I go, that's our template. And as such, we need to measure its pixel length and width. Boom, we've got it. Now we know that, we can now look at any object as long as they're at the same depth. If this pixel to millimeter ratio is a certain amount, this will have the same one. So if this is 75 pixels and this is 150, we do a quick mathematical calculation and we can know the height and width of this object. And then we can do the same for the top and we're able to measure an object. And that's how my system works. It's being able to remove tedious tasks and remove this complicated system and just introduce it to be completely automatic. Like even while I was doing my project, Amazon released their own system of a robotic arm that was able to detect objects and move them. But they worked on a different principle that I see to be a critical error. They worked by having to take pictures of every single object from all angles and have someone measure the length, the width, the height, the weight, how fragile the item was, and input it into the system, which is not removing the task of packing, it's just swapping it for a different task, just for the robot to try and identify this object, and was still only able to identify about 50% of the catalogue, because the catalogue is millions and millions of items. We all know Amazon has millions of items, and thousands of new items are coming on and off every single day. So by having this system that they developed, it's got a massive critical failure. It's not able to recognise every object. Well, my system doesn't care about what the object is. It doesn't go, oh, what is this? Is it a hairbrush? Is it a dog toy? It doesn't care. It goes, let's find out the dimensions. Let's pick up this object. And as such, computer vision can do this. This computer vision is a powerful technology that can do everything. It's going to be the future, and it's becoming the future of technology. Once I had this futuristic technology in place, this packing system in place, I then wanted to integrate a user interface so that if this was to be sold or introduced to a factory, it was able to be interacted with, it was able to be tweaked and to have that user input still. And so even though it would work autonomously, you can still tailor it to your personal preferences. As it is a modular system that's able to be slotted into any system, regardless of their feeding item, their output item, this would be able to detect its size and interact with it. As such, I integrated the user interface that was able to have the user interface where you could see the actual camera feed. It had buttons where you can tweak the speed, you can change the accuracy, and it had a self-diagnosis system, which is a personal system I added in late into my project. It was nothing to do with any of my deliverables, but something I wanted to add in. And this was using computer vision to diagnose issues, to see that why is my system not working? And rather than having, I don't know if you've seen any of these videos where a factory fails and all the items get pushed onto the floor because a bolt's come loose and it just doesn't know there's an error and it's pushing all the bottles and they're smashing onto the floor. Rather than having that, we can use cameras to detect that something's going wrong. Is it a personal issue? Is the claw not grabbing it properly? Does the claw need to move? Or has something happened where the conveyor belts leaned and they're all sliding off? As such, is able to detect these issues using cameras. and then act accordingly. Can it try and fix it, or does it need to alert this and stop the system, alert the technician to come fix it? This is how my project works, by having the system that is able to detect and interact with its environment using cameras, and represents the future of what computer vision can do. Where you can imagine you work in your local store, your local shop, and every single building has a camera in the corner, if it's a factory, if it's a school, whatever, and you could determine if everything's working okay, if anyone's trying to steal, if there is a heart attack that happens. It would be able to detect this in the environment and act accordingly if it needs to start up the defibrillators or turn on the alarms. You can have computer vision detect all these amazing things. And as such, this shows the representation of what computer vision can do and the future it has. One thing to tell you that my system works amazingly, but it's another thing to validate it. As such, so much testing was done throughout this journey, from testing of how strong the components were, including the 3D printed parts, testing how accurately it can measure objects, and also various testing of saying how often can it pick up the object, how often can it successfully identify the object, and how successfully is it as a whole. And as such, so much testing was done to validate it working in every single stage. Here's before I even had the Qt widgets involved, and I was still testing every single situation and documenting it, and proved that it worked in over 98% of all scenarios. And even further, I even tested the user interface with regular people and engineers to make sure they can understand it, and tweaked it and fixed all issues so everyone could use my system, and tested successfully. Overall, I've developed a system that not only has succeeded all the plans of developing a system that is able to recognize objects, pick up these objects, and interact with the environment smartly and use smart computer vision techniques, but also have more advanced features like self-diagnosis and the ability to tweak settings and really have a true user interface, not just simple flashy buttons, but true interfaces. And I've also integrate advanced safety features where it's able to have buttons that will shut down the system, and even detect if a human hand's put into place using YOLO vision, and able to detect human hands and stop the system so your hand doesn't get stuck. These are going above and beyond my initial deliverables for this project, and I'm able to introduce a whole system that works effectively and is powerful. And I'm very proud to say that I've finished and worked hard on the Fiddy ARMOR project, and has great future applications as well, as next I'm going to be working on a feeding system that is able to feed different items onto this. Even though my dissertation is over now, I'm going to work on this to be able to have a fully automatic system, a fully enabled product that can go to different people, and items can be fed on the conveyor belt, and also it will be able to weigh these items, and it will be able to print off the labels and stick onto it. But due to the Wi-Fi capabilities of the Raspberry Pi, you can have your store on a website, and someone can type in their name and address and press purchase, and the system can start packing your objects automatically. So you could be out in town and you come back and suddenly all your items have been packed and ready to put down to the office, and you haven't had to do anything. Straight to the post office and you're done. And that's the future of Fiddy ARMOR. The computer vision is going to take over the world and be in everywhere, and I'm glad to say that I'm going to be at the heart of automation. And I would like to thank all the people who've helped me with my work, all the technicians in the Plymouth University and all my lecturers who have come to advice and have taught me stuff over my time at university and taught me the valuable skills I need. I would like to thank my supervisor who helped challenge me and come up with new ideas and find out a true representation of computer vision. I'd like to thank all the engineers I've spoken to in the interviews I had with both students and people in the workplace, and about how the real issues affected them and how I could change my system to be fixable and modular and be easily understood for people who aren't robotic engineers, people, just the average customer, the average person. And I would like to thank you for watching this video and supporting me and being there for my journey. And I love computer vision. I want to say that it's been a great part of my life, and I'm looking forward to working hard on it in the future, and I have plans to keep journeying on my computer vision journey. And I'll say thank you for watching Fiddy ARMOR.